Want to talk a bit about Clifford algebra as it relates to physics and the standard model. So this is also referred to as geometric algebra. I prefer to just call it Clifford algebra though, because there's some things with geometric algebra. There's like a sub-community that let's say regular physicists don't really like to associate to. So it's unfortunate. It's just mathematics. It's really, you can think of it as the mathematics of matrix algebra, but and that's good enough. It's just non-associative algebra, right? So first, I just want to go through a quick introduction to the topic of the mathematics itself, and then we're going to pivot to a variation of this mathematics that one can use to describe the standard model. Okay. Again, it's actually quite simple, so most modern physicists will probably look at this and go, oh, you know, this is easy. And that's kind of the point, really, frankly, is that it's easy to understand. So in reality, the Dirac equation, when he derived that, he stumbled into Clifford algebra and sort of reinvented it from scratch. Had he known about Clifford algebra ahead of time, which predates him, but it's you know, at that time there was two different groups and there wasn't a lot of crossover. It would have been easier to get at to the Dirac equation. But let's just get into the basics. We'll start with, I guess we could start with R3, right? But the reason why this is referred to as geometric algebra is because it provides a mechanism by which to describe geometric objects in an algebraic way. Okay, so let's get into it. I'm going to describe it geometrically, and then you might have or a line. It's a plane. Oriented, meaning that it's a plane, but also with a direction. If you're familiar with computer graphics, you already understand that concept that a plane has an orientation. You can start with a point. Let's say if I have a triangle, A, B, C, you can think of it as if the orientation is A, B, C, curls, pokes out of the board. If you reverse the orders, it physically looks like the same plane, but then it would be pointing in this direction. So this is an orientation of the plane. Okay, these are called bivectors, by the way. But the idea is that they represent planes with an orientation. It's important to know that orientation in computer graphics because when you're rendering three-dimensional objects, they're made up of little triangles. I need to know which way is out versus in 3 dimensions. And then you, of course, can go into higher dimensional elements depending on the dimensionality of your space. In 3 dimensions, we only have one left, which is called a pseudo scalar. So we're looking here at R3 as our first example, but there could be any number of dimensions. 1, 0, 1, 2. And this represents the volume. Okay. The idea of the Clifford algebra is very simple. It's built on a very simple idea. Okay. We're going to create a base element of a vector space. And in this case, sigma 1, sigma 2, and sigma 3, x, y, and z. Okay? These objects are non-associative geometric objects, which means that sigma 1 times sigma 2 is not the same as sigma 2 times sigma 1, for example. Okay. So what is the rule, though? And this is where the Clifford algebra part comes in. The rule, sorry for blocking this. For R3 anyway, is as follows. Okay? So, as an example, sigma 1, sigma 2 plus sigma 2, sigma 1 is going to be 0. And this is true for any two indices that are not the same. When they are the same, 1 squared, you get it twice, so the 2 drops, and this is the Kronecker delta, so this is just 1. So that's true for all 3 of these. So when you square them, you get 1. Okay? That's the rule. So what we do then in this algebra is we construct objects out of all possible combinations of these, or what are referred to as the generators. But really, you can think of them as the unit vectors in a vector space. Okay. So let's draw the total object as combinations. Right? So you have some scalar element, has no generator elements, plus let's say A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3. Of course, you could use a summation notation to make that easier. There's a vector in 3-dimensional space. Now we do our bivectors, A1 2 sigma 1 sigma 2 plus A1 3 sigma 1 sigma 3 plus A2 3 sigma 2 sigma 3. Sometimes this is written in reverse order. Won't get into that. And then A1 2 3 sigma 1 sigma 2 sigma 3. That's the total number of combinations there. So an object in this geometric scheme is defined by a total of 8 individual functions of the space. Okay. Now I'm using sigma in particular to represent these generators because they are, in fact, the Pauli matrices. It can be represented in matrix format in that way. So I could write them as matrix format like this. Okay. And that gives me back the same algebra. Okay. And that's it. So in a nutshell, this is all we got. And then you have that rule that, like I said, so when you square any one of these, you get 1. And then the order of multiplication matters because they're matrices. They're represented as matrices in this formalism. However, pure mathematically, you don't need to use matrices. They're completely defined by that algebraic rule that relates how you multiply them together. That's it. It defines the entire geometry. There's a lot of cool things that you can do with this. This is 3 dimensions, it's fine. This leads inevitably to a relationship between 3 to SU2. If you're familiar with physics, you're aware of that and the double cover and everything that's involved there. That's already well known. The interesting thing comes, of course, when we go to R4. And then we use gammas to, so in R4, we have our generators are the gamma matrices from Direct's equation. And the rule that we write is gamma n plus gamma n, gamma m, so reversed, is equal to 2 GMN, which is the metric tensor, or the Minkowski. Okay. So now taking the same concept that we had in R3, which allowed us to describe planes, lines, scalars, and volumes, and now we're bringing it into R4. And this algebra is fairly well understood, of course. What is interesting, though, and the reason why I even want to talk about all this, is you can introduce curvature into this algebra, right? How would one do that? Well, again, think of what these generators are. So in 3 dimensions, we had our sigma 1, 2, and 3. There's a 4th one for time, but I can only draw 3 because, you know, it's hard to draw. So in space, we would have let's see, this is again 1, 2, 3. So x, y, and z. What happens when there's curvature with the vectors like this? Well, that might be the curved version of that unit vector. And then as you move around in this space, because of curvature, you might get something that goes in a slightly different direction as you move around, because that's what curvature is, right? So each one of these is going to be describable as a Lorentz transform in curved space. Now, to be fair, and we all understand this, that type of transformation only works locally, meaning, within a region of the point that you're analyzing. You can essentially absorb the curvature into the redefinition of your unit vectors as long as you stay within a small neighborhood of the point. That is the case, right? As you expand outside of it, then it diverges, and it's not a good description of that anymore for all cases. Okay, this is well known already as well. This is what I hope wir I'm trying to learn German, so E-I-I-E. In any case, so what that means is this. If I have the curved version of some generator, it's going to be a linear combination of the flat Minkowski versions of that generator. Okay. So because every vector can be written as a linear combination of a basis. So we're just changing the basis back to the flat space version just around the point that we're looking at. And that gives us the curved versions. Okay. And the rule, because this is what it is then that I'm skipping steps, but metric tensor is described as a square of these things, and I'll use that to represent the Minkowski metric. Okay. This is what allows us to do things like spin connections, which is a way of writing the Dirac equation eventually for curved spacetime. Okay. It's a simple procedure. We're moving the curvature into the unit vectors. Why does that matter? Let's run through a simple example. Let's suppose we want to look at electromagnetism in curved space. Well, the electromagnetic field is a vector, a 4-vector. So we're going to create this is a Clifford Algebra object, and I'm going to use a summation notation and write it in this way. This is what a vector would look like in a Clifford Algebra. It's just the 4 elements times the 4 generators. But now we know that this thing is not flat. It's changing throughout the space. It's important. So what about a derivative operator? We can do that too. We can create a derivative operator, delta, which is also based on our Clifford algebra. And then we can look at, well, what would that operator on A look like? So let's write it out. I'm going to use a different indice here, keep them nice and separated. That's what that would be. Okay, well, we know we have the derivative of this and this, because this is no longer the flat version. Let's write that out in all its gory detail. Wonderful. So what about this? The derivative of the unit vector. Interesting. So there's going to be up top, down below, too slow. right? What does this mean? I'm not even going to define what that is, but if you're familiar with general relativity, you know what it is. This means that the derivative of our unit vectors that are varying throughout the space is going to itself be a vector. And there's some linear combinations of the basis at that point that describes the derivatives. Derivative of a vector is a vector. We can describe it as some generic linear combination. Okay, so plugging that bad boy in there, we'll get gamma alpha, gamma beta, alpha, mu, that's this first term, plus gamma alpha, and did I screw that up? Yeah, I did. Thank you. Right, so delta alpha, when written out in its terms, looks like this. Well, this is symmetric, so that you can reverse. Again, we're just doing it's symmetric because that's symmetric. What about this? Well, let's go ahead and write a symmetric version of it. I'm gonna do some tricks on this so you can see, even though tricks are for kids. So all I've done here is I've written it twice. That's why we get the 1/2, and then I just swap the indices. You'll see why in a second. Well, we already know this from the rules of our Clifford algebra that is the metric tensor, right? So we can write this first term like this. Okay, so this term reduces to this. Again, 1/2 gamma alpha gamma mu, this part here, is equal to G alpha mu minus 1/2 gamma mu gamma alpha. All from our Clifford algebra, a rule, the singular rule that defines the whole thing. So the first part, this becomes plus G alpha mu d alpha mu dx alpha. And then we have a minus 1/2, which same thing as here, right? So that then means we get plus 1/2 gamma mu gamma alpha alpha minus d mu dx alpha. We're almost done with this. This is anti-symmetric in mu and alpha. So if we divide and do a bunch of maneuvering, we get that, and now it's 4 of them. So this last term in its kind of final Super Saiyan form looks like this. They're mathematically equivalent to just illustrating the full anti-symmetric nature of each element. Okay. What is this? Well, this can be rewritten as dA mu dx alpha plus gamma. Let's say lambda here. So we're swapping out the betas for the mu's. So this object here, just really simple to write. In full tensor notation, looks like this. This is a Clifford algebra object. It's fully anti-symmetric. This represents the bivector. Sometimes you'll see it written like this. That represents the bivector element here. And then there's a 1/2 because You have to divide by half for this. This is, of course, what we already know from electromagnetism. It's the field vector. This is just the covariant derivative, and with the g mu nu, this condenses to that. Okay. Typically, we set this to 0 as a gauge condition on our electromagnetic field. Now, notice it's the covariant derivative as regards curved space. That just comes with the entire package because we're using curved gammas. And this is a term that we're going to label F. F equals del A equals, if we set this to 0, we just hit this 1/2 mu gamma alpha F alpha mu. The ordering matters because you have this anti-symmetry. You have to be careful. Cool. Why is that cool? So what? F gamma mu gamma alpha. Well, you can imagine what we're trying to do here. We're trying to get to Maxwell's equation, written in this Clifford algebra format. This is generally covariant. To make that clear, this is the version of these equations in curved spacetime. To be honest, does it look like it matters whether it's curved or not? No. If you were to just treat gamma as if they were the Minkowski gammas, you would get the non-curved version. It's the same equation. Point being that this formalism allows us to write equations much like with tensor equations, where we know it's covariant right out of the gate. So we don't have to worry about what happens when you change space-time coordinates. So naturally, the next step is to look at the derivative of f, applying the same thing. Of course, that would just be del squared of a. You can guess where that's going, right? That's a long calculation. But I'll just say that through that calculation, you're going to get something akin to, and you can certainly look this up online, there's lots of references to this, something akin to, let's say, alpha, beta, delta, alpha, beta. There's lots of notations for derivatives, so I'll just delta plus beta delta x alpha plus alpha dx beta. These are actually covariant derivatives you can insert in there, but the gammas disappear. So this volume element, 3 in space-time, times this, and plus some constant I'm leaving out because I'm being lazy. So reduction alpha beta dx, jeez. Yeah. Sorry. Alpha, beta. Let's get there on. Okay. And actually, this ends up being alpha, beta, covariant derivative with alpha. That's what it is. So an area element, since we're adding, something proportional to a vector, when you multiply, an area by a vector, you're going to get some of it that becomes a vector, so they reduce. and some that expands into the volume. Right? So that's what you end up getting. Well, we can set this equal to a source vector, where J is the current. So that means Maxwell's equations look like this. Because you have the vector element here equaling this vector element, and the volume element here equaling 0. So all of Maxwell's equations in curved spacetime is this one singular equation, which, if you really want to work with A, reduces to this. That's Maxwell's equation. Okay, so that's fun with Clifford algebras for R4 for spacetime. And you might say, okay, great. What about spinors? Let's talk a bit about spinors. That was just dealing with the vector. But a total object in this Clifford algebra has scalar, area, and pseudoscalar, which is the 4 volume elements as well. Here's an interesting thing to know, by the way. The pseudoscalar element, u, lambda, gamma nu, lambda, gamma alpha, lambda, gamma beta, and we have to do all of this with the constant in front of here, 16th. Mu, nu, this is some totally anti-symmetric element, meaning it's really just a scalar in fancy format. This will reduce once you do the math, and I'll lay it out for you later on, but this all the way down to minus, well, that's the determinant of the metric, so if we're doing it in curved spacetime, 0, 1, 2, 3, and we'll just label this A, 1, 2, 3, right? Whatever that element is. It's totally anti-symmetric, so it doesn't matter. Key element here is that you get the determinant of the space-time metric in that part. So in the prior example, I'm dealing with F star F is the Lagrangian of the electromagnetic field. Okay, what's F star? F star is F itself times I inverse. What is I inverse on the right side? Remember, order of multiplication does matter here. I is the pseudoscalar element of your chosen Clifford algebra. In this case, it's gamma 0, 1, 2, 3. Okay. So I inverse is whatever that is. In this case, it's going to be minus gamma 0, 1, 2, 3. Because when you square this, you get -1. So this is the Hodge dual. In Clifford algebra, Hodge dualing is like taking the entire algebra and flipping it so that your pseudoscalar becomes your scalar and your scalar becomes your pseudoscalar. Right? So that in our case, vectors become volumes, volumes become vectors, and the area elements change places with one another. That's what that right multiplying by that. That's the effect that it has on our algebra. Okay? That's what a Hodge dual ends up being. So the Hodge dual of F times F gives you a Lagrangian, which we already know we carry one of these over thanks to this term, which is part of the Hodge dual itself. So you get this, and then you end up getting the vector form of that. Okay. And then there's, of course, like a 1/4 and blah, blah, blah. I'm leaving out a lot of the constants because going through all of that just consumes too much time. Okay. So back to spinors. What we're going to do now is look only at the even subalgebra. So the A+ algebra is what it's referred to as. It's a full subalgebra because an even element of the Clifford algebra times another even element gives you an even element. Two odds times each other give you an even element. So they are not a group. They're not a subalgebra. Okay. but A plus is. So this is A plus A. Let's try to keep consistent here. The area, and then again that pseudoscalar, which again we can just rewrite this, save ourselves some time, and do the darn thing, write it out. Okay. That forms the subalgebra, and this again we're sticking with space-time algebra, R4. This is a spinner. This is the electron field. That's what it ends up being. If you were to write this out in matrix format, using the gammas as the matrices we all know and love, this would look like, and I use the while convention where the left and right are separated out. So not the direct convention. And that's really important to do because later on, the whole point of all of this is to break down this standard model, and the standard model cares about chirality. So in matrix format, that's what that looks like, where psi 0 and 1 are the spin up, spin down components left-handed, 2 and 3 up and down components right-handed. So we have 4 complex numbers that are constructed off of, there are 6 of these, 1 of these, and 1 of these, 8 real elements. That's that. You can then use that to guide you in drawing out a Dirac equation. That's what that looks like in Clifford algebra format. Same del that we had before. Psi, whatnot. You might be saying, well, wait a minute. Doesn't that mean, because this is constructed off of these curved gammas, that this del is going to have, the Christoffel symbols, the curvature, space-time built into it? The answer is yes, but it's tough to write this in the generalized format to make it look, and this is the format, by the way, if it were, let's say, not curved. How do you get from the curved to the not curved and do that? That's where the tetrads come in, okay? And because of that, what ends up happening is this has to be adjusted including this interactive element omega, which is tied directly to, it's called the spin connection. So let's go through that a little bit. All right. So as before, the del operator looks like this. And then we have psi. Right. Well, psi is this. So we know that we're going to have some elements dealing with the derivative of that. Tell you what, let's do it differently. I'll edit that out. All right. Where does this come from? How do we determine what omega is with this schema? Well, one thing we have to talk about is what is psi in the sense here of this algebra. Let's do this. Let's create an operator called tilde. And what this does is it reverses order of multiplication. So if I have gamma A, gamma B, and I tilde it, I get gamma B, gamma A. That's what's all we're doing here is taking the elements of each one of these and flipping their order. Okay. And because of our rule, we know that in the case of the areas, that gives us a negative. In the case of this, it stays the same, and of course, in scalar stays the same. Okay. So what we're interested in then is, I'm going to call something j, and it's going to be psi. And I'm going to multiply it by gamma 0 tilde. As you can see already in this matrix version of this, we have star elements in here already. It's built right in. So I don't need to take the complex conjugate anything here. I've got both the spinor and its complex conjugate sitting there. Okay. So what does this look like? Oh, interesting. Well, right? 0, 0. We write it in matrix format. Becomes apparent. In the while formalism, gamma 0 looks like this. What does tilde look like given this construction? It's just reversing the area elements. I'll try minus 1. I'll have to edit this down because this is gonna I have to pull this from memory, which is insane. Psi 3 star and psi 0, right? And the psi 0 star and psi 2. Minus psi 3, right? Psi 3 times psi 1 star, okay. Yep, that's what it is. And if you really want to do that exercise to prove that you can, trust me, bro. So doing this multiplication, this is really just the identity and the identity. So this identity is pulling that up. This one's pulling that down. So you get psi 0 star, psi 1 star, minus psi 3, psi 2, psi 2 star, psi 3 star. 0, 0, and 0. So this times that gives this, so that times that. What does that look like? What is this times this? Oh boy. Doing standard multiple matrix, we get the side 0 squared plus the length of side 3 squared. One star minus side 3 star. Right. Isn't this fun? Yes, sir. And something similar over here. Point being this. What's cool is then if I break that down as a linear combination of our gamma matrices in the while formalism, we immediately get that J0 here as defined is 1/2 third element. Minus 1 squared minus 2 squared. Look familiar? Yeah, it's the probability current. And similarly, you have plus and minuses going on here, and trust me, you get the right answer. It works beautifully, okay? Again, we're trying to figure out what's going on here. Why does this matter? Well, it matters because we're interested in torus transformations, okay? How do you transform an element in a Clifford algebra? I'm not saying coordinate transformations, I'm saying transformations. Any object, let's say it's J prime, is going to equal R is what's called a rotor. It's a rotation. Okay. Again, it's an even element. This is an odd element, but even to cancel, so we'll get an odd element out of it. Vector becomes another vector. Okay, so that's plugging all this in. R psi gamma 0 R tilde R tilde. So a rotor applied to our current vector has this effect. And this is very familiar. Sometimes S is used when you're, R is always what's used here. You can rewrite it like this. So clearly the effect of this rotation on J is the equivalent of taking psi and performing that operation on it. Okay, cool. So this is a Lorentz transformation, isn't it not? We're doing rotations or Lorentz transformations in space-time. Boosts, if it's one of the elements of the rotation, is time, and just regular rotations of both space. Fine. How do we factor in this R then when we're taking the derivative? Well, that's why we have the omega there. We want our equation to be invariant under these rotations. So R is often written like this. E to the omega mu nu times gamma mu gamma nu. Well, these are some functions over the space. So this whole thing up here is an even element. And again, I'm omitting constants, okay? Which is why then this omega from our derivative here is proportional to this. So it's some constant times something like this. That's called the spin connection. That's like a gauge, coordinate transformation version of how you derive what omega is. Equating it to the Christoffel symbol and all that jazz is its own discussion and is pedestrian. You can look it up. It's nothing new to our theory. Right? We now have a Clifford algebra way of identifying what it is, where it comes from, and why it's there. Okay, and it ultimately derives from, I want this to transform in a way that I expect a vector to transform in my Clifford algebra. Okay? So J is a vector, even though it's constructed out of this thing that I made out of an even subalgebra element of the space. Okay, so we square this object with something in the middle, and it gives me a vector of space-time. This is important because this singular equation actually allows us to create the entire standard model later using a different algebra, but using this exact same formula. Okay. We want this to transform as a vector. That's the key. It's kind of a mapping between whatever the heck this is to a vector in space-time. And that'll be the case no matter what the space is. Okay? Now, why are we doing any of this? It looks like we're just recreating stuff that we already have models for. Maybe they're less elegant in some sense, right? Lots of pieces inside of them have to be individually put into our standard modeled Lagrangian. Why are we bothering this, even though it looks pretty? Who cares about how it looks? If it predicts the same thing, who gives a crap? One of the things that I want you to keep in mind here, classically, this is just a column matrix. Right? So you have psi left, psi right, or psi left spin up, psi left spin down, psi right spin up, psi right spin down. 4 complex numbers in a stack, looking like a vector, but for a 4-dimensional complex space, right? In a Clifford algebra, this thing can be multiplied not only by the left by a bunch of matrices, which is what we have in the classic direct equation, but also on the right-hand side. You could think of it as its own, expanding this to its own matrix if you want to, but the geometry there allows us to put in curvature into all of our generators and create a covariant derivative with that curvature in place that'll contain not only multiplying on the left, which is what I showed you just a moment ago, but also multiplying on the right. Let me show you what I mean. Let me write that equation again. J is psi 0 psi tilde, right? And instead I started with a rotor on this bad boy, so that R was on, on the left here, and hence the omega. But instead of starting with J, let's start with psi. Let's say that psi prime is, in this case, I'm going to use L instead of R to represent Lorentz, and then right multiply by something called U. We don't know what U is, but we're allowing the transformation of psi to have both a left and a right element now. Because you can do that in Clifford algebra, which you could do in the standard way of doing things. How does J transform under that transformation? Easy to do. Interesting. Again, our singular rule is, I want this to transform like a vector, because we defined it as such. It is a vector in space-time. So our rule for U looks to be this. And that leaves us with this. Well, this was the original J, right? Okay. What's J? J is actually this, right? So this last rule, and I won't expand on it because it becomes important later when we change our space, really it could be written like this. L. So we'll just pull out the constant element that's summed over. So you have this rule for U, and this rule, to make it a vector, has to be some linear combination of the original gammas, so that this then becomes J mu gamma alpha mu alpha, okay, which is what we would, and lambda is going to look something like this. Okay. So this is the Lorentz transformation rule. That limits what L can be. That's important. That limits what L can be, because it needs to follow this pattern. That limits L to being a Lorentz transformation. And we're dealing with space-time algebra. That's all you get out of it. There's no additional transformations that we can squeeze into this rule that come out of the symmetry. Okay. This guy means that there's an internal transformation going on that we don't even see. It leaves J unchanged. What are some examples of what might work here? Again, it's a rotor, meaning it's it has to be an even thing. And that's certainly the case because we're multiplying it by something like this. Well, how about, and I of course I know the answer, so I'm going to give you some examples. E to the alpha of gamma 1, 2. What is that? Well, you know, you can just write it out. So 1 plus alpha times gamma 1, 2 plus alpha squared over 2 factorial. Gamma 1, 2 squared is actually negative 1 plus alpha cubed over 3 factorial. Right? But then we have this minus gamma 1, 2 plus alpha to the 4th over 4 factorial. Right? Simple expansion. You should recognize this. These elements are cosine. These elements are sine, but with a gamma 1, 2. So we get gamma 1, 2 sine of alpha. That's a type of U. What is utility? Well, that just flips it. And when you flip a even thing, you get a negative. Okay, so we're going to have cosine alpha plus gamma 1, 2 sine of alpha. Gamma 0 cosine alpha minus 2 sine of alpha. Does this equal gamma 0? So does it qualify? Squared alpha times gamma 0. This times that times that. This times this times this. Right? Minus cosine alpha sine alpha. Gamma 0, 1, 2. 0, 1, 2. We get 1, 2, and 0 here. Plus cosine alpha sine alpha. Gamma 1, 2 dot gamma 0. This is a shorthand, by the way, for gamma 0, gamma 1, gamma 2. Okay. But you can rearrange this very easily. Again, using our Clifford algebra rule, and you get this. So those obviously cancel. And then the last term is minus sine squared alpha, gamma 1, 2, gamma 0, gamma 1, 2. Again, I can just move this over. Because when I move it twice, it flips signs twice. This is squares to negative 1. These canceled. So I have cosine squared plus sine squared times gamma 0. So it's gamma 0. So this equals gamma 0. Checkbox. Yay. So this transformation is safe. Okay? It solves this particular condition. So what the heck is that? What would that look like? Not to whisper like Joe Biden. What would that look like? Remember that before when we had r here, then we had a modification to the derivative. So we're going to have a new modification where we're right multiplying by something that's proportional to gamma 1, 2. So our new derivative, let's use delta to represent the Clifford algebra covariant derivative. It's going to equal our standard derivative, right, plus the spin connection, which is gravity, effectively, plus psi. Now we're multiplying on the right. Gamma alpha, because that comes from this here, some unknown field, because we're allowing this alpha to vary throughout the space, gamma 1, 2. Okay. Of course, I'm giving you the answer here. It's the electromagnetic field. In other words, this internal transformation in space-time algebra leads to the electromagnetic interaction. Okay? Or if I were to write this out entirely, right, you would have the following. I'm using shorthand. What does gamma 1, 2 look like in matrix format? Again, I use, right, so sigma 1, 2 on 1, minus I. So it's I minus I, that's sigma 1, 2. So we get minus I minus I. Man, I'm getting sloppy. There you go. Right multiplied. Point being, there's our imaginary number that we know will end up in this for the electromagnetic interaction has an I in it. I'm leaving out constants here, like E over H bar. There you are. You say, well, yeah, but what's going on? Well, remember what psi looked like, right? When I wrote it out in matrix format, we had psi 0, psi 1, minus psi 3 star, psi 2 star, right? Right multiplying. It's real important to remember that. Psi 2, psi 3, psi 1 star, psi 2, psi 0 star, right? So that's going to multiply the first column by minus I. The second column is going to get a multiplication by just regular I. Regular I, whatever that means. So it's a flip of the I's for the regular elements versus their complex conjugates, yeah? Which is expected, complex conjugation. And if you write out the full Dirac equation and all its components, this gives you exactly what you would expect from something with electric charge. There you have it. So that is space-time algebra version of Clifford algebra. We have curvature, which we carried over very simply. That gives us our spin connection. We even have, if we expand our transformation to a right-handed multiplication, electromagnetism. Cool. That's not the standard model. It's a very limited subset of the standard model. Sorry for flying through that. I'll probably make some more videos and dive into a lot elements of these in more depth. I'm just trying to get to the weenie, so I'm trying to blow through all of this as quickly as possible. Okay. Love this. This is going to give us everything. It's weird that this is the case, but let's get to the weenie. We want to go to a different kind of algebra entirely now. Space-time algebra is great and all, but it certainly doesn't have enough room to fill in all the spots for the standard model. I'll try that again. There's not enough room in space-time algebra to deal with the entire standard model. At best, you can play around on the fringes and try to insert extra space for one more spinner inside of there. And you can even play with that U element that we just talked about, and you get some elements that look like the electroweak interaction, but they're not all the way there. Because that U that I wrote, that was proportional to gamma 1, 2. Actually, there's other elements. I'll tell my mom. There are 4 elements that work. So you're like, oh my God, electroweak theory, electromagnetic field. This ends up being, so these combine in essence to be B alpha and W alpha 3. These elements combine for W plus or minus alpha. Right? And they kind of do, except it doesn't work, right? It doesn't work. I mean, the interactions are there, but it doesn't give you the chiral nature of everything properly. I've played with this, don't worry about it. It doesn't quite work. Okay. You have to make additional assumptions about this transformation in order to get it to work. There's a paper by Hestenes where he tries to show that. and he has to insert additional fields, and it doesn't provide anything of value to do it that way. It isn't quite right. What we really want is a transformation or a rule that's very simple and compact, that's going to give us the chiral nature of the standard model, to give us the lecture week like out of the box without us having to fudge anything or play around with anything. It's just very obvious and apparent. So what we're going to do now is we're going to go to a different space entirely. Instead of R4, we're going to go to C4. What the heck does that mean? Ooh, this is different. There's a thing about complex numbers is that they have a conjugate. If you want your space to be analytic, then you have to make sure that you have a separation between Z and Z star for any of the elements. So Z versus Z star, right? I should not be able to transform one into the other through like a rotation or some sort of transformation like that. Because if you can do that, then Z is nothing more than R2. It really is exactly equivalent. It's R2 in disguise if there's some transformation, I don't know the notation for this, that isn't complex conjugation. Like complex conjugation is the only way to go from here to here in an analytic space. Okay. There's Cauchy-Riemann and a bunch of restrictions on the space that make it analytic, but this ends up being the case in an analytic space. No rotation takes this, and that's very important because that'll limit. Remember, rotations from our prior discussion, those give us forces, or give us gravity in the case of Lorentz transformations, or the internal rotations gave us electromagnetism. So you can expect that the forces of our new space are going to come out of rotations, and we don't want a rotation that allows this to happen. If you did, it'll be easier to see once I get there, then you would have all kinds of problems. You would have quarks being able to turn into leptons, which we know doesn't happen, okay? But all of that, those restrictions that don't allow for quarks to become leptons, mathematically comes from this condition, which is that our space is complex, but it's analytic. All right. What are the generators? First, we'll talk about the generators of a complex dimensional version of the Clifford algebra. I label these with Q. So we have Q1, or 0, 1, 2, and 3, like we had with gammas. Okay. But again, we also have the paired up version with the other side of things, which is the conjugate space. So we really have 8 generators for our space. Wild, right? 4 complex dimensions gives us 8 generators. What is the rule now? Well, Q, and I'm going to raise the index here, Qm, Qn plus Qn, Qm, the 2SMN, which is a half of the metric. It turns out in complex spaces, you can support 2 metrics. Qm, Qn dagger plus Qn dagger, Qm is equal to Gm, and I put a bar over the n to represent the conjugate elements. There's an entire tensor calculus that one can make about this. So if you really don't like Clifford algebras, we could redo the entire thing in tensor calculus and give it curvature and all the fun stuff that comes with it. So if I have a vector, for example, in this tensor calculus, it of course has its complex conjugate, which all I do is I put in a bar over it. It just makes it the notation easier to work with. If I have a tensor with 2 elements, Of course, I also have its complex conjugate, which is borrowing both elements. But then I also have a mixed element, where you just borrow one of them. This entire set is all of the metrics of the space. Okay? So a vector, the metric, that's the tensor version. In the Clifford algebra version, you have this. Now, this ought to look familiar, and it's not a mistake that it's familiar. Another condition of our space is that this is true. And now, and in flat space, so when there's no curvature, the G, M, N bar is 1/2. Okay? So this is our flat, no curvature version of our space. This is the space we're constructing, now the world that we're creating for the standard model. This is the geometry of the standard model. This is the algebra of the standard model. Okay, and I'll show you why in a bit. These conditions are known. That this is what we would expect from creation and destruction operators. So our generators of our space have the same algebra as creation and destruction operators in flat space. And I say in flat space because here's the other thing. QM is equal to EMA QA. There is no term like this. If there was, then there would be a way to morph a creation and a destruction operator together, or Z and Z star. So because it's analytic again, that term is gone. Q is only a linear combination throughout the space. This is a tetrad in our complex space, and it's restricted like this. Okay. What it means, again, is our rotors are only rotors that allow Q, the different Q's, to transform into each other, but not into the Q daggers. Not allowed. Otherwise, it's not analytic. There's a connection between what I just did and this condition as well. So they're all related to one another. Okay, but S is 0. The interesting thing about it is, because of this condition, S is always 0. Why is that important? Well, these are creation destruction operators. That means that the exclusion principle, which derives from this condition that this is 0, is true in all spaces, no matter how curved they are, no matter what the geometry is. You still cannot have fermions in the same space, or in the same state rather. Not possible. The other thing to keep in mind is, typically this is equal to 1, right? And in this case, it's the delta, it's 1. If we have curvature here, wouldn't it be possible then to have more than 1? Yes, but we're going to introduce another element to this space called conformal. Kind of important. Why? Because we interpret these objects in this space, they're quantum fields. They need to be able to operate in such a way that we don't have 1.5 particles, and we don't allow that to be the probability of finding a particle state in our system to be 2 for a single particle state. That wouldn't make any sense. And the way that's done, because these are creation and destruction operators, is to scale this bad boy. So you have to be able to scale the metric here in such a way that it gives you the right probabilities. It's just kind of built into how we'd expect quantum mechanics to work. So our space is what? C4, analytic, and conformal. Okay. Maybe I'll do a little talk about the math of all of this later if anyone's interested. But this is the way that you deal with it. All right, so let's just write it. And I'm going to absorb that 1/2 in here for now and get it in a format that we're familiar with. Okay. Cool. How do we identify states? Well, because these are creation and destruction operators, it's actually fairly easy to create states. So here's the deal. So let's assume that we're working in the flat version, so that we're taking the curvature out of our cubes and absorbing it into the elements. Okay. Again, we'll just work in the flat space for now. This is 1 in the case when this is even. So what that means for our space, Q0, Q0 dagger plus Q0 dagger, Q0 is 1. And that's true for 0, 1, 2, and 3. Okay, so if I take this construction and multiply them all by each other, I get 1. 1 is equal to, and I'm going to use this notation, okay? So, because again, we're lazy. Okay. This represents that. The curly brace will have a minus sign in it. We're familiar with that, I hope. Right, obvious. 1 times 1 times 1 is 1. This gives me 2, 4, 16 different elements if I read it out individually. So let's do it. Not all of them, but you'll get the idea. Q0, Q0 dagger, Q1, Q1, 1 dagger, Q2, Q2 dagger, Q3, Q3 dagger, plus Q0 dagger, Q0. This one flipped, and then this all again. 1, Q2, Q dagger 2, Q3, Q dagger 3. Plus blah, 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 16 of them. Here's the cool thing. We're going to label these V1, V2, all the way to V16. If you add them all together, they equal 1. So we have sum I equals 1. 16 of VI is 1. VI squared is equal to VI. So we'll say this is an idempotent element. Again, you can think of them as matrices. Not hard to see. If it were 16 by 16, V1 is just that. V2 would just be this, right? If you add all of them up together, you just get the identity matrix. And if you square any one of them, they get itself again. And they are orthogonal. That's it. This is lovely because this means we can multiply any generic object in our space by the sum of all of these elements, and I can break up the entire generic object of the Clifford algebra space that we're dealing with into 16 states, each with 16 elements. Okay. So let me give you an example of one of these elements. We'll call it psi1. So psi is sum I equals 1 to 16 psi I times vi, or psi times vi, excuse me. I'm going to write out one of them. Again, we're taking the even subalgebra as we did before. Okay. So our space is like the even subalgebra. We don't want to do the half. We could talk about that later. So let's just take the first element. A1 plus B1, 1, Q0 dagger, Q1 dagger. We're going to break this up very intentionally. Okay. Plus C1 plus D1, C1 Q0 dagger, D1 Q1 dagger, Q2 dagger. So scalar, area, area, area. E1, Q0 dagger. D1, Q1 dagger. Or F, sorry. Keep my daggers right. G1, H1, Q0 dagger, Q1 dagger times Q2 dagger, Q3 dagger. Okay, and all this times on the right hand side, B1. Q0, Q0 dagger, Q1, Q1 dagger, Q2, Q2 dagger, and Q3, Q3 dagger. And then there's 15 more of these with some of these flipped until you get to the bottom ones are all flipped, and these are all flipped. So how do we go? 1, 2, 3, 4, 5, 6, 7, 8. 8 unknowns. Now we're dealing in a complex space, so these are all complex valued functions. Interesting. What's interesting is that you have this structure here, and this structure would look the same if I just pulled the Q3 out. So you can rewrite this as E1 Q0 dagger plus F1 Q1 dagger, right? Plus G1 Q0 dagger, Q1 dagger, Q2 dagger times Q3 dagger. Okay. Nothing new. I'm just moving it around so you can see that we're getting something kind of repeated twice with a Q3 dagger. How interesting. What would a rotation, let's say, in the 2-3 plane look like? So we'll do a little foreshadowing here. It's going to be some sort of like once it's in the derivative, we know it'll look like, I don't know, some x alpha, and it'll have a Q2 and a Q3 dagger. That's what a rotation looks like once you break it out in pieces. So this would be a rotation in the 2-3 plane, as an example. And of course, as before, you can either do that from the left or from the right. We know that we're going to have different rotations on left and right like we had before. Our equation for our vector is going to be as it was before. Same thing. Now, that leaves open what is gamma 0. We'll get into that. But we have a similar situation going on here. So if I had a rotation in the 2-3 plane, this is one way of doing it. You, of course, can rotate the other way. Well, how would these rotations impact these states? Well, as you can see, one thing I want to point out, and this is important to know, that Q2, Q2 dagger, Q2, Q2 dagger. So if you square it, that's the same as doing this as squares to itself. If I have Q2 dagger, Q2, Q2 dagger, well, this is 1 minus the flip. And whenever you have two of them next to each other because of this condition, it's 0. So this just is equivalent to that. So there's steps to reduce all of these different combinations of the generators, okay? It's similar to what the gammas, but a little bit different because of this rule when they're the same. So what happens then, you can see if I take 2 and 3 dagger, multiplying by this one, this portion here, I'll have a 2-2 dagger, which will vanish because it gets absorbed into my element here, and this gets replaced with a 3 dagger. So that's the equivalent of taking this element here and moving it over here, and this has the effect of going the other direction. This one has no 2 or 3 daggers, so it's equivalent to trying to multiply my element here by 2 or 3 dagger. You're going to have a 2 and a 2 that line up, and so it'll equal 0. So this rotation will only rotate then these two parts into each other back and forth. These are not affected. Okay. On the other side, if you're rotating on the right, you can see we have dagger, 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 dagger. So this particular element, V1, doesn't rotate ever. There's no rotation that has an impact. It stays the way it is. Excuse me. But later with the other V's, there are elements where the 2 and 3 are flipped, and then they will rotate into each other. So we have a situation where this rotation is going to move only part when it's on the left, and only certain elements on the right. Columns, rows. So let's get into this element now. Now we know how this lays out, we can try to get an understanding of what all these different states might mean. In order to construct a current vector, then I need to have some kind of mapping between what the gamma matrices, the generators of space-time, with these generators of this complex dimensional space. So we're just going to pick one because we have a sense and we can kind of figure this out. I'll write it out for you. Sorry, Q0. There you go. So we pick 0 and 1 out of our 0, 1, 2, 3 and map them to 0, 1, 2, and 3 of the gammas. You can see from here that this has the following relationship, 1, 2, and 3. Switching between them. It also has all the proper rules. Q0 squared is actually this, which we know is 1. Gamma 1 squared is minus -1 and so on. So it has the proper signature of space-time algebra. This works perfectly. Here's the thing. Knowing this now, let's look again at this rule and look at the generic rotations that we talked about before. What is J prime L psi U gamma 0 U tilde psi tilde L tilde? Just like before in space-time algebra, nothing new, but now we're working in the different bases. So as before, our rules are and L gamma mu L tilde has to equal some linear combination gamma, so that it's a Lorentz transformation. So that J transforms like a vector. That's it. Interesting. Now remember, L and U are rotations so that, and limited to, the Q's do not rotate into the Q daggers. Doesn't mean the rotations themselves don't contain both Q and Q dagger elements. In fact, you need both in order to achieve that rotation, which we can go through a small exercise to prove, but rotors, mixed. There's our rules. What do we know here? Well, gamma 0 is this. It contains elements of Q0. Well, if that's the case, then all of my U's are only rotations then between 1, 2, and 3. Q1, Q2, and Q3. I don't know why I put that there. Right? So we know that U are rotations in 1, 2, 3 only. Okay. You can't involve any rotations that involve 0, because then gamma 0, then this would not be true. You can't rotate something that's purely in 0, mixing 0 and other things and get it to work. That does not work. What about the Lorentz transformations? Well, there's the set, of course, that we already know that apply to the gamma, so this is between 0 and 1. But we're in 4 dimensions, so that means L is gravity, or Lorentz, well, let's just call it Lorentz plus rotations in the 2 and 3 plane. Because there's no 2 and 3 here. So I can include L's, which are rotations of these gammas, in the 2-3 plane. They'd be unaffected. So they'd be equivalent of this being 0. So those would be like internal rotations, because they don't affect space-time at all. And we just went through an example of a 2-3 rotation, where it took this thing which had 8 elements and flipped half of them with each other and left the other half alone. What does it sound like? Well, okay, rotations in 3 dimensions, you mean SU3? Rotations in 2 dimensions, you mean SU2? Yes, one caveat. There's also the neutral rotations that you can do in a complex space. Neutrals will look like this: 0, dagger, minus 0, dagger, 0. Right. That's an example where you're just using the same. You're rotating within the plane. That rotation has the effect of doing a phase transition. So that rotation will take, let's say, Qj to e the I theta times Qj for some j. Those are what we will label the neutral rotations, because they give rise to neutral currents. So in this case, what you have, when I say SU3, you have 6 rotations, 1, 2, 1, 3, 2, 3, and then back again. That's 6. And 3 neutral currents, so we have to cross that by U1. This also is crossed by U1. And these are, let's say, prime and double prime. Okay? Because we don't know yet whether the U1s that we know and love from the standard model. Oddly enough, whatever U1 is going to end up being is going to be a combination of these two. Some from the left and some from the right. And then you have standard SU3, along with standard SU2. That's a standard model. That's it. All from this condition. So if we don't want to talk about gravity, we'll just omit that for now, which would be the equivalent of just treating this as if it were a condition like this. And we're good to go. So let's dig into it. You can see that this only works because of the number of dimensions that we've chosen. If you were to add 5 dimensions, or 6, or 8 in the complex space, then this condition would expand to include rotations that don't have any physical meaning. There would be new forces that we don't have any explanation for. And if you reduced it, then you would have an equal problem on the other side, where you wouldn't have enough room. This is why when I first wrote the space-time algebra, I said, hey, this looks like electroweak theory, but I said it didn't work quite right. That's why it didn't work. Okay. So I want to restate real quickly what it is we're doing here in a nutshell. We created an algebra in 4 complex dimensions. We demanded it to be analytic and conformal, which restricts the types of transformations that we can perform on objects within the space, analytic in particular. Okay. We've then added curvature to the space in the same way that we did with the space-time algebra. We did that to tetrads of a metric tensor. That then allows us to create a spin connection. But now we're doing it in our complex dimensional space. So we've added geometry to our space. Everything's geometry here. That creates an altered derivative, a covariant derivative, that contains elements that come from the geometry of the space. But in the case of spinors, it's a spin connection version as opposed to a vector conversion version. But it's, again, in a complex dimensional space. And those covariant derivative elements that come from the geometry give us the forces within the standard model. The Clifford algebra limits the number of states that are available to us. So unlike the standard model as it's written now, which is fun to play with, and you can throw scalar fields at it, and you can add different various things to see what works and what doesn't, and play around with it. Our theory doesn't allow room for that. There's a limited number of possible states within the geometry of what we're working in, dictated by the generators themselves. All the forces are generated by geometry, and the states are limited. So it predicts quarks, it predicts leptons, it predicts the chiral nature of the electroweak force. It predicts SU3, not SU4 or SU5, right? All right, so let's get into this. It's interesting. Because SU2, the right-handed rotations are SU3, aka 1, 2, 3 only rotations, right? What are the states that, even despite this, won't have SU3 interactions, right? Based on how we understand what these rotations look like. Remember, these rotations look like this. So they're going to have a Q1, Q2 dagger, or Q2, Q1 dagger, Q1, Q3 dagger, Q3, Q1 dagger, Q2, Q3 dagger, Q3, Q2 dagger. Okay. So what are these? These are the gluons with color. So the color changing gluons. Again, we're just multiplying on the right side. So because of the nature of our generators, these won't work if I have a situation where all 1, 2, and 3 line up in their structure. So let me pick an example. And then of course you have the 0 part here. Whatever this is, it doesn't matter because it's not part of this interaction anyway. So there's 2 of these, right? Dagger, 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 all on the right. If you right multiply by anyway, you get 0. And then, of course, the opposite. This also gives you 0. Right, so there are 4 rows in that construction I showed you. There's 1, 2, 3, 4 that have no interaction with colored gluons, which therefore are lepton states. Okay, those are leptons. All right. Now, within those, like we saw, remember when I wrote the matrix for a standard spinor, you saw, this is in space-time algebra, or, sorry, 2 and 3. Notice that these all double up, right? In matrix format, okay? So that means the same state is going to appear in its complex conjugate, is going to appear in our total object. Same thing happens here. And so what ends up, even though you have 4 rows like this, it really represents just 2 particle states. What we think of as 2 particle states, electron and a neutrino, okay? That's what you get. You get an electron and a neutrino. This is one generation of particles that we're just going to deal with one right now. I'll do a whole separate series on mass and the Higgs and the different generations of particles. Okay, but right now we'll just stick with one. So these 4 represent these 2 particles. Well, then there's also, of course, the flopping around of these maybe I flip one of these, Q2 dagger Q2, instead of that. So that it's, well, that's a colored state, because I can multiply this by Q3 on the right anyway, Q2 dagger. What would that do? That flips these two. So that would then become Q2, Q2 dagger, Q3 dagger, Q3. 1 is unaffected, 0 is unaffected, and then this would push those out. It's effectively how it works, and so you end up with on the inside. So remember, psi is on the left here. The individual states are on the left. So if I multiply the whole thing, this whole thing on the right by this, it has the effect of flipping this to a different V. So this might be V3, and this becomes V4, and then we have this pushes through and flips the different states inside of here. Okay. So that's a colored state. And the structure is all there to do it. Now let's look on the left-hand side, which I said was electroweak. Gravity too, but again, we're omitting that for now. And this is why I wrote it that way, the way that I did. We can look at a lepton state. A plus B, Q0 dagger, Q1 dagger, plus C, Q0 dagger, plus D, Q1 dagger, and Q2 dagger, plus A, Q0 dagger, plus B, Q1 dagger. I'm using capital letters now for the second set. C plus D, Q0 dagger, Q1 dagger, times Q2 dagger, Q2 dagger. So while multiplying on the right changes the B states, multiplying on left keeps it the same row, but it starts flipping things around. And like I said, a 2-3 transformation is going to rotate these into each other. So what is it that we're going to call these 4 sets the electron? We're going to call these 4 sets the neutrino. And this is the left-handed part of the neutrino and the left-handed part of the electron. Right-handed, right-handed. See what's going on here? So this electroweak rotation, which is a 2-3 rotation, flips not only the isospin, right, states, but only the left-handed parts. So the chiral nature of the electroweak force is built right into the restriction of rotating only in that plane. That's it. I don't have to throw any 1 plus or minus gammas or any extra jazz into my Lagrangian later when we write that. It's built into the very structure that was of what came out of that one restriction for that vector, is the projection from this 4 complex dimensional space down to something that exists in space-time, that it behaves like a vector. That's it. That's all. And we have this structure. Okay? Now, that carries through, including the quarks, which are going to be the up and down quark, of course. And there are 3 color states, red, green, and blue. So you have something similar going on. There are different combinations, but the same fundamental structure. Let's go ahead and, using the gammas, which I'll remind you what they are, look at what the Dirac equation might look like to verify that we're on the right track here. So I can properly label these things, and I can prove to you that this is in fact what's going on. So if you take these and multiply them by the derivative to create the del operator, we're just going to look at del, forget the interactions for a moment, till I get something that looks like the Dirac equation. So let's just look at the neutrino. We can also do the same for the electron if you want. And say, well, what is A, B, C, and D? Are they indeed, we're predicting that this is the left-handed and this is the right-handed elements? Is that what we get? Okay. Sure, well, if I take Q0 dagger plus Q0 times D0, so what's the derivative operator if I write it all out? Minus Q1, I Q1 dagger plus Q2 plus Q0 dagger minus Q0 D3. That's this derivative operator. And I left multiply it on that bad boy. What do we get? Again, we can only get combinations of 0, 1 daggers here. Anything that's 1 dagger or just 1 without the dagger gets eliminated by our V1 projection operator, so those don't count, they won't work. So really, but if I multiply by Q0 here against a Q0 dagger, that gets eliminated, and we still have a 1 dagger. So there's this algebra that you have to factor in. Well, let me write it all out. We're going to get D0 plus D3. Give me a Q0 dagger on A. To get a Q0 dagger here, we have to multiply Q1, which gets shifted 1, therefore with a negative sign. So we're going to get plus D1. That negative, but that shifts over. Similar going on here, minus ID2 times B. And that's a Q0 dagger. So this operator on this gives me one possible equation here. Similarly, I'm interested in the 0 and 3 combinations on this guy. 0 minus 0, that eliminates that. So we're going to have D0 minus D3 times B. And this will end up being the Q1 dagger. What's the Q1 dagger on A? D1 plus I. So D1 plus I, D2 on A, excuse me, on A. Okay, so this operator on this, looking at this part, gives me these two equations. Looking at that, and knowing what from our head and memorizing what the direct equation is in the while format, I know exactly what this is. A is equal to psi 2, and B is equal to psi 3. Well, these are the spin up and down states for the right-handed part of a spinner. So this is, in fact, as we just proved, the right-handed part. Okay, cool. What about the other side? What about this applied to here? So I'm interested in a 0 dagger with a 1 dagger, but I want to flip it so it's 0, 1, and not 1, 0. So I'm going to have minus D1, because we want to flip it, minus ID2 of C. This will give me my, and of course times Q2 dagger. Now what's the state on this to give me this? And I need a 0 dagger, so that's plus D0 plus D3 D. So I'm doing this math real quickly. I apologize if it's hard to follow, but trust me on this. Trust me. And then we want to do that version. So I need to hit this with a 0, regular Q0, so I get D0 minus D3, 0 minus, let's see, and then D1 plus minus D1 plus I, D2, D. Okay, what does that look like? Where's this coming from? Well, that means that D is equal to psi 1, and C is equal to psi 0. If you know the Dirac, again, if you know the Dirac equation by heart, you know that that's the case, which are, in fact, the left-handed states. Crazy. Psi 0, psi 1, and 2 and 3 were over here. How does one get the spin? What is the spin? What is S3? Spin 1/2 what? Well, it's usually 1/2 is minus I gamma 1, 2 over 2. What's that? Well, that's actually this operator. With the q's. Or written out just like this. Right, over 2. Of course, we love our 1/2s, don't we? Okay. What would that give me? Well, remember what's over here. We have Q1 and Q1 dagger in our V. So when there's no operator, that's going to give me spin up. So it's a spin up. Because of the Q1 dagger here, we have to reverse it, spin down. No 1, spin up. A 1, spin down. As predicted. So this does in fact give us the Dirac equation. This d psi acts like what in this space acts just like the Dirac equation with these gammas. In fact, the Dirac equation I wrote before, if you want to look at the mass term, still applies in this space. It works the same. Works identically. Again, we're ignoring this for now, because you have to do more with this. After all, you have a whole lot of particle states in our object now, not just a singular mass. And we have a whole lot more interactions. So, if I write this as gamma mu d mu psi plus, now we're going to write it like this. W is just the 2-3 rotation stuff, which also includes 2 neutral currents. We can add the rotations between these, which gives us gravity. We're not going to worry about that too much right now. And then there's the right versions, which are all the rotations between 1, 2, and 3 on the right. That's our Gluon field. Okay. So we define that this way. I'm just going to write it as a mass term here. And again, this will end up being some operator. It's a little far more complicated than this. That's your Dirac equation now. It's invariant so that psi prime equaling L psi u produces the same equation. Okay? We can multiply this gamma 0 out, and get a formula for something that looks like a Lagrangian here. I might get a plus or minus around in here, I apologize. That's your mass term in your Lagrangian. So we're going to have something that kind of looks like this, but this, again, is a Clifford algebra object, right? This is the thing we're trying to minimize, containing all these elements. Well, as you could guess, we can do this twice and get out elements of this that look like field elements, curvature, space-time. So Lagrangian is going to contain some sort of combination of field elements. I'll leave these constants unknown for now. Matter, mass, that. Once we figure this out, you can guess that there's going to be some additional elements in here that deal with whatever the heck this is. Since it looks like psi squared, you can guess that it also is derived off of the metric tensor that we talked about before. The curvature of this complex space is going to manifest itself in this, which looks an awful lot like what one would expect if I had, remember, G, M, N bar, if I'm writing it in tensor notation like this, that's the length squared of a vector in a complex dimension space where S part of it is 0. This is not flat. Then it's going to have a determinant. Well, guess what? That determinant also makes its way into here. In complex dimensional spaces, the volume element is proportional to the determinant of the metric, not the square root of the determinant of the metric. But remember, there's a tie. You square the vector to get this J element, which is in space-time. So likewise, the determinant is a square root is related. This ends up being the same. Okay, I'll get into that later. So you do have a curvature element in here that one would expect. All coming from this geometry. So everything stems from that. These elements come from that. What does this look like? Let's pick the smaller of the two. Let's review that real quick. Well, they're based on rotations. What are the rotations that are available in the 2-3 plane? There's e to the I alpha of Q2 dagger. Here's the neutral currents. E to the I beta, Q3 dagger, 3 dagger, Q3. Rotations that are only in the 2-3 plane that don't involve daggers. E to the I lambda. Let's see. Yep. Q2, Q3 dagger plus Q3, Q2 dagger. Dagger this, you get the same. You can need a minus sign. Everything has to be unitary. E to the omega with no I. Q2, Q3 dagger minus Q3, Q2 dagger. Those are your 4 rotations in the 2-3 plane. So the same sort of thing is repeated for gluons, but you have 6 of these instead. So you get 6 of these, and then you have 1, 2, and 3 of those. Happy fun stuff. Right. These then can be written out in their long form rotations, but ultimately what you get is the following. Each one of these varying throughout the space of your field, and you of course have all these i's, and then you have I, let's say B. I might get these confused with one another. Something of this structure. I, and we're just going to strategically label these. And I'm leaving out the coupling constants. In fact, let's combining these together, you can see an I here and a non-I here that creates an element where this might be, let's say, W, I think it's 2. So we have plus I, W alpha 1, Q2, Q3 dagger, and then of course the opposite. There's that minus sign. I, there's 2 I's here. I. So I'm pulling out the I, I'm being intentional about all that. But you can see how that works. So this W mu here, again, ignoring gravity, right? So ignoring this can be written in this format. Now I may have the coupling constants off by 2s or 1/2 or something like that. It's pretty easy to, I'm just freeballing this based on what I remember. So I do have the specific one right now. That's just a lecture week. There it is, in a nutshell. 2, 3. So you're going to get different combinations of these two based on this will affect left versus right-handed, because we saw that earlier. This will affect isospin up and down. So you're going to get different combinations of these neutral currents. From the left, remember that U1 element is also from the right, okay? So you're going to see this bad boy again, coming from the right. And then the weak currents. So then if you go through and you try to calculate this, which is a derivative of these things, and square them, if you run through the insane amounts of Clifford algebra, matrix multiplications, whatever you want to call it, you end up getting the exact right answer. What is interesting though, so I was like, okay, great, where's the new physics? If there is any. Well, one, theory predicts a right-handed neutrino. It predicts that that right-handed neutrino doesn't interact with anything other than gravity. So if it exists, we know that that's true. The other interesting thing is, because that U1, the correct full U1, and by that I mean the electroweak hypercharge U1, is a combination from both of these things. What that means is that you're going to have some interesting constants in front of here to make everything wire together and to make it work. So there is a bit of new physics there, because the constant in front of the gluon element of this contains parts that look like this. It's not this. It's this with some small adjustments. That's it for now.